Assalamu alaikum everyone. Today I am here for our project on weather prediction. So basically this is an machine learning project. So for this we are using an Arduino Nano. So what is an Arduino Nano? It is the brain of our weather prediction system. It reads the data from other sensors like temperature, humidity and air pressure, then processes this data and set into the laptop or computer where you want to display. It sends through a USB port. So we can say that Arduino Nano is a small microcontroller which takes the data and display it or send it to the laptop. So basically the first sensor is DHT11. So DHT11 is our temperature humidity sensor. It measures the temperature from the surrounding and then sends the measured temperature to the Arduino. Arduino Nano uses this data for the prediction and for monitoring. So why we are using DHT11? Basically it is a low cost and also it's so the next sensor is a BMP180. It is basically a barometric pressure sensor. It measures the air pressure in the atmosphere. It sends the pressure data to the Arduino. Air pressure helps in the predicting weather changes. BMP is basically a small and it is also a very low cost. And also it works very well with Arduino for the prediction or accuracy. Now we are moving for the most important step, that is of wiring. So for this we first take DHT pressure sensor. So basically in this we have the three parts. First is of VCC, then data, and then is ground, and of course we have three parts of the wire. So the ground, you can here see the ground will go in the ground port of the Arduino Nano. So basically here we put the ground, and then we have our data. So the data will move in D2 section, and I hope that my cameraman is showing you the right ports. And at last we move the VCC into 5 port, which is present here. So that is all for the HTTP now we sensor. Have a BMP sensor, and in this sensor we have 4 wires. The first is of VIN, the second is ground, third is SCL, and the fourth is SDA. So starting with VIN, which has a red wire, it will go in 3V3 that is present on the second last in the Arduino. So we put it here. And then for ground, that is of green color, it will move in the ground like this. And then we have SCL that move in A5, which is of a light yellow color. So here we have, and then for SDA we go to A4. This is of A4. Now we have successfully connected our both sensors with the Arduino, and now through a USB port I will connect this with my laptop and we will produce a live data. So I will take the USB port and connect it to the sensor, and you can see a red light blinks on the Arduino. It's mean we have successfully created.
Now I'm going to explain all the coding. So right now, as you can see, this is the code that we have compiled on the Arduino, and we have like used the default libraries for DHT and BMP. With the help of this code, after every 5 seconds, the Arduino is inputting the data of temperature, humidity, and pressure. But it was the raw data, and as the C-OM port is connected to the Arduino, so we are basically running a Python script just to save that data onto a CSV file. And we also like we can't use any other library in Arduino to use the correct time. So we are using timestamp, the datetime module, so that we can input the correct time, as we are going to use year, month, minutes, everything like that as our features labeling. So with the help of this, we are getting like this type of data. So I'm gonna run it for you guys. As you can see, currently like our project is connected, our Arduino is connected, and the CM port is connected. So I'm gonna run. We are using UV as a Python as a package manager. So don't worry about that. This command, and I'm gonna run it. So I was not in the correct directory. Let me go into the correct directory. Now I am in the correct directory. So now, as you can see, it is saying that it is connected to CM, and the Arduino is sending temperature, pressure every 5 seconds. And as you can see, like this is the data that Arduino is sending, and this is the CSV file, and as it is going to update every 5 seconds. As you can see, there was then only 41 last night, it is 42, now it is 43. So in this way we are getting our live data
All
from
right, let's
Arduino.
dive right into this explainer. Today, we're mapping out the complete architectural journey of a machine learning model, taking it all the way from training to deployment. If you've ever wondered how abstract data science code actually transforms into a rapid, deployable product, you are definitely in the right place. We're going to treat this almost like a manufacturing process, visualizing exactly how the heavy mathematical lifting gets done under the hood. Here's our blueprint for today's session. First, building the random forest. Second, evaluating our performance metrics. And finally, Joblib serialization and deployment. Basically, we'll be following a strict three-step life cycle. Think of it like an actual factory flow. We train on the factory floor, we evaluate in quality assurance, and then we serialize for shipping and logistics. Keeping this high-level structure in mind is really going to help anchor you as we get into the weeds of the algorithmic details. It's just train, evaluate, and serialize.
Okay, step 1, building the random forest. Let's get to training the algorithm.
So, the real magic here? It's all about the ensemble. You know, instead of relying on just a single fragile decision tree, which is notorious for just memorizing training data and completely bombing in the real world, this approach groups multiple trees together. By building a whole multitude of trees during training and then averaging out their predictions, the algorithm inherently stops overfitting in its tracks. It's a massive boost to our predictive accuracy.
Let's look under the hood at how this actually works with the hyperparameters. To optimize its learning capacity, we set our first hyperparameter and estimators to exactly 100. This dictates that the forest will build exactly 100 independent decision trees. By having 100 separate voices contributing to the final answer, we're ensuring a highly robust aggregate prediction.
Next up, we set max depth to 12. Think of this as putting a hard limit on how complex each individual tree can get. By capping each tree at a maximum of 12 splits, we prevent the model from getting too bogged down in the training data. It essentially forces the model to maintain its ability to generalize to unseen inputs, making sure it finds real patterns instead of just memorizing the noise.
Then we lock the internal random number generator with a random state of 42. Now, while 42 is a fun sci-fi reference, this setting is actually an absolute must in machine learning. It guarantees perfect reproducibility across different training runs. Because building these trees naturally involves a bit of randomness, locking this state ensures that if you run this code tomorrow or a colleague runs it next month, you're getting the exact same 100 trees every single time.
Finally, configuring n jobs to -1 acts as our massive accelerator. Training a complex ensemble of 100 trees is seriously computationally intensive. So setting this to -1 explicitly tells the algorithm, hey, break out of single-thread processing. It utilizes all available CPU cores on your machine. It's kind of like opening up every single checkout lane at the grocery store. It significantly speeds up the entire training process.
All right, part 2, evaluating model performance metrics. Let's move over to quality assurance.
So, how do we actually grade this thing mathematically? Consider this table our performance scorecard. We're using 3 standard regression metrics to rigorously put our predictive accuracy to the test. Let's break down exactly what each of these distinct metrics is telling us about our model's health.
First up is MAE, or mean absolute error. Honestly, this is probably the most intuitive metric we have. It simply measures the average magnitude of the errors in our predictions. If you're predicting house prices in dollars, your MAE is in dollars. It gives us this beautifully clear baseline view of our error margin in real-world units without overcomplicating things.
Next is RMSE, root mean squared error. Now this one is a bit more ruthless. Because it squares the errors before averaging them together, RMSE slaps a much heavier penalty on larger discrepancies.
It shines a harsh spotlight on any extreme outliers or massive miscalculations our Ensemble might make. If your model gets most things right, but completely blows it on a few predictions, your RMSE is going to spike way higher than your MAE.
And finally, we look at our R-squared score, or the coefficient of determination. This measures the proportion of predictable variance in the target variable that we can successfully explain with our input features. A score closer to 1.0 means we're highly effective at explaining those underlying patterns. That missing slice of the donut? That represents the variance we can't explain, just the unavoidable, chaotic noise of the real world.
Section 3. Joblib Serialization and Deployment. Time for shipping and logistics.
Once we have a model, we need to preserve it to disk, a process known as serialization. Now, standard Python does have built-in serialization for basic objects, but it really falls short here. Joblib, on the other hand, is specifically engineered to handle the massive NumPy arrays that make up the internal structures of scikit-learn models. A random forest of 100 trees is fundamentally a giant collection of heavy matrix data. Joblib is the specialized tool we need to handle that efficiently.
This brilliantly illustrates the transformation. By running a joblib.dump command with a compression level of 3, the massive computational weight of those 100 intricate decision trees gets efficiently crushed down. It turns into a highly compact, lightweight joblib file. We're literally taking our massive factory and shrinking it down into a portable little shipping container.
And that compact footprint isn't just about saving hard drive space, it is functionally crucial for deployment. It allows a user-facing platform, like a Streamlit web app for example, to instantly load those pre-trained weights directly into memory. That means when a user inputs new data, the app can generate real-time predictions instantly, completely bypassing the massive computational overhead of having to
Shown you
retrain the
guys
model from
that
scratch.
an animated video about this model, like why we're using. As you can see, we are using in model training.py, in which we train all the data. This was our final data in data.csv, and we are using sklearn, random forest regressor, and we are using mean absolute error, mean squared error, and R2 score for collecting just to examining the accuracy of our model. Right now we are loading our CSV file, and then we are checking the error if the file is found or not. Then these are our feature columns that with the help of these we are going to use, which we are going to predict from our model. And here we are inputting all of our data, feature columns, and then we are splitting them, and then we are like telling on the terminal like what is the data. And then we are also training each model. We are using random forest regressor. Regressor is actually used for calculating, is used to calculate on numeric values. That's why we are using regressor. And random forest we are using, it is basically decision trees, and you can guys, we already explained in our animated video, you can see that. And now we are, after like building every model, we are also making telling us about what is the accuracy of each model, what is the mean absolute error, what is the root mean squared error, and then we are saving model in using Joblib. And after Joblib, we have our main.py. In main.py, we are building a simple, we have just built a simple streamlit.app. And then we are defining a process file in which we have like run a basic Streamlit command in which port which to run and in what address to run. And we are basically hosting this website on Heroku and project.yml and uv.log. As I already told you guys, we were using UV for the package manager, and it is the built-in files or everything. Let me run you guys locally first our app, then I'm going to show you our live app. So currently it is running, and now you guys will see our app is running, and now it has opened. This is our simple Streamlit app that we have made. Now it is just loading model, as we were using cache decorator for the Streamlit app. Now we can input anytime, we can input any date, and we just have to click on generate prediction, and it is going to predict our. As I was telling you, we also have live hosted our app. So this is the URL you can guys visit on, and this is our live. It is live. You can go and put anytime, any date, and you can check out like our